Good morning, class. Today we will be studying how to find the MGF of a normal distribution. Um, so, as we all know, we all by now know what is the PDF of a normal distribution, and we have studied the properties of MGF. So, using both of them, we shall see how we go about getting the MGF of a normal distribution. So, as we all know, we shall first state what is the PDF. So, if x follows normal between mu and variance sigma square, then we know that its PDF fx is given by 1 upon sigma root 2 pi e raised to minus 1 half x minus mu upon sigma the whole square, and most importantly, we should know the range of these random variable x and the parameters mu and sigma. X is from minus infinity to plus infinity. Mu, the parameter, is from minus infinity to plus infinity. And sigma, the variance, is always greater than 0. Sigma standard deviation, the square of it is a variance, is always greater than 0. So this is the PDF, we know about it. Now we also know the properties of MGF. MGF means moment derivative function. So the MGF for any distribution is defined as mxt is equal to expectation of e raised to px. This is the way we define MGF, we know about it. So here we are talking about a continuous distribution. So when I am talking about expectation of e raised to px, this should be equal to the range of x, whatever is the range of x, e raised to tx, fx, dx. This is the way we would define the MGF for a continuous distribution. Here we are talking about the normal distribution, and therefore MGF or MXT is given by integration. What is the range of x for us over here? It's from minus infinity to plus infinity. So integration from minus infinity to plus infinity. E raised to 2x. F of x. F of x is the PDF. What is the PDF? We have written the PDF, so we take it down here. It's 1 upon sigma root 2 pi. E raised to minus 1 half x minus mu upon sigma the whole square dx. So this is the way the MGF, we're going to start off with this coordinate and we're going to derive it down to a particular formula which we will be using always whenever we're talking about the MGF of a distribution. Now over here 1 upon sigma root 2 pi is a constant. It can come outside the integral and we will be left with the remaining things. So what are we left with? If I push this 1 upon sigma root 2 pi outside the integral, then my next step, I'm going to do it here itself. My next step would be this is equal to 1 upon sigma root 2 pi. It is a constant, it comes outside the integral, and I'm left with these things. Now over here I see that I have x minus mu upon sigma the whole square. I have a huge number around there. Let me bring about a transformation. Let me say let x minus mu upon sigma be equal to z. I'm going to call this term that I have as the power of e. That is the power of e over here. I'm going to call it as some z. I'm going to bring about a transformation. If this is so, then x can be written as mu plus sigma z. Now we know that x is a value between minus infinity to plus infinity. So whenever x takes the value minus infinity, z will also be minus infinity. Whenever x takes the value plus infinity, z will also be plus infinity, and therefore the range of x, when I am taking the transformation that x minus mu equal sigma is equal to z, I see that the range of z is also between minus infinity to plus infinity. X can be written as this, and when I take the differentiation of this, I get dx is equal to sigma sigma dz, because the variable over here is z. Mu is a constant out here when I'm trying to bring about this time. And so I'm going to plug into this equation that we had with us. Into this equation, I'm going to plug in these values. So wherever I have x minus mu upon sigma, I'm going to replace it with a z. Wherever I have an x, I'm going to replace it with mu plus sigma z. And wherever I have a dx, I'm going to replace it with sigma dz. I hope that's fine with everyone of us. So I will just erase what I wrote at the top so that we know when I input these values how do they look like. So just bringing about the linear transformation. Therefore, my mxt, when I'm calling x minus mu upon sigma as z, it would turn out to be 1 upon sigma root of 2 pi. The integral, the value of the integral is from minus infinity to plus infinity for z. So I keep it as minus infinity to plus infinity. Instead of e raised to tx, I'm going to change my x as mu plus sigma z. So it's going to be e raised to t mu plus sigma z. And into e raised to, this entire thing is going to become a z. So it's going to be again write as minus z squared by 2. And instead of dx, I'm going to write it as sigma dz. I hope everyone is fine with this. So this was the original MX, the MGF. Here we substituted the fx value. We brought about the transformation. So instead of having x now, I'm going to have things in terms of z. And this is what happens. So with your permission, I'm going to erase this off, because whatever we have done here is projected out here. And now let me look at things clearly. I have e raised to tx, e raised to t mu plus sigma z. In that this mu and t are constants. The variable out here is z. It is z that is moving from minus infinity to plus infinity. I can take that outside the integral. Also, I have a sigma here and I have a sigma here. They will be cancelled. So what am I left with? I am left with, I can say this becomes e raised to mu t upon square root of 2 sigma integration minus infinity to plus infinity e raised to t sigma z. The base is same, the base is e, so the powers can get added. That's minus sign, so it's going to be minus z squared by 2 dz. And this can be further simplified as I can write this as e raised to mu t upon square root of 2 pi. We know that whenever in statistics we are dealing with the e raised to something, we would always try to have e raised to minus terms. We will keep e raised to minus, I will take this minus 1 upon 2 constant outside, and e raised to minus 1 upon 2. And what remains inside, it will be z squared minus 2 t sigma z. I hope the equation holds, the clarity holds out here. What have we done? We have taken minus half constant outside, and so this is the transformation that will happen in this equation. Now, let us concentrate on this term that we have over here. I can look upon this term, whatever I have over here. This is z squared minus 2t sigma z. I can consider this to be the first and the second term of an expansion, which is z minus t sigma the whole square. So if I have z minus t sigma the whole square, let's expand it. What are we going to get out of it? So this is going to be equal to z square minus 2 sigma t, 2z sigma t plus t square sigma square. So what I have over here are these two terms, right? So I can replace this. I can replace z minus e sigma the whole square minus e square sigma square. I hope you all are understood it. This happens to be the first term and the middle term of this, what do you call it? If I expand the z minus e sigma the whole square and expand it, I can make it like this one. And the first and second term is same as what I have over here. So I can write this as e raised to mu t upon 2 pi minus infinity to plus infinity e raised to minus 1 half power, and I'm going to write this as z minus e sigma the whole square minus e square sigma square. I hope it's fine with every one of us. So this term that we have over here, I have simplified it into this. When I do it, how is it going to help me? This t square sigma square is a constant, it doesn't have z in it. It will come outside the integral, it will come over here. And I'm left with a term which I can very well just bring it down to a standard normal variant. And the integral from minus infinity to plus infinity, the standard normal variant would be equal to 1. So that is what I want to get to that level. And so, with your permission, let me just erase the previous steps. So, this was the last step that we had in this. So, from here, we have this. This is a constant, and as I said to you, I'm going to take this t square sigma square outside the bracket because it doesn't have a z term in it. And so what am I left with? I'll be left with e raised to mu t. This is a minus sign, minus into minus makes it plus. So I'm going to get a plus 1 upon 2 t square sigma square. Or I can write t square sigma square divided by 2. I can write it that way. I can write it as u2 ut or ut plus t square sigma square divided by 2. So e raised to ut plus t square sigma square divided by 2 is constant upon root 2 pi. Integration from minus infinity to plus infinity. What is left? This term is left. I have moved this term out. This term is left. So what is that going to be? It's going to be e raised to minus 1 half z minus t sigma the whole square dz. Right? I hope this is fine with everyone. We just thought about some transformation, and now I will see ways to solve. What I'm left with this term, and now I'm saying let me call upon z minus t sigma. What I have is a z minus t sigma. Let me call that as some other variable u. So let z minus t sigma be equal to u. Now if z is from minus infinity to plus infinity, u also will be, whenever z takes the value minus infinity, you will take the value minus infinity. Whenever z takes the value plus infinity, you will take the value plus infinity. So the range of u also happens to be from minus infinity to plus infinity. Okay, and so that is how we get this value of, we've taken about this transformation, we've called it as u. And dz, when differentiating it, this is a constant, t and sigma are constant, differentiating with respect to z, I'm going to get it as du. So, how will this equation now look? So, I have the constants e raised to mu t plus t square sigma square by 2 upon square root of 2 pi, integration minus infinity to plus infinity, e raised to minus u square upon 2, right? Because this term, I've called it as u. So z minus t sigma whole square is going to be u square and du. Now, what is this? Does this ring some bell somewhere? What is this thing? When I have 1 upon 2 pi, integration from minus infinity to infinity, e raised to minus u square upon 2 du. What is this? This is the PDF of a standard normal variable. This is a PDF of a standard normal variable, and I am taking the integral from minus infinity to plus infinity. By the law of physics, we know that over the entire range, the PDF value is equal to 1, and therefore this entire thing is equal to 1. It implies this thing is the standard normal variable, PDF of a standard normal variable. When I'm integrating from minus infinity to infinity, I'm taking over its entire range. The area under the curve for the circle is equal to 1, and therefore this term vanishes because it's equal to 1. Now what am I left with? I am left with the nxt, that is the moment generating function, is e raised to mu t plus t square sigma square by 2. So this is the way we get the moment generating function for a normal distribution that has the mean mu and variance sigma square. So I hope you have understood how we derive the moment generating function of a normal distribution. If I want to talk about the standard normal variant, what happens in standard normal variant? In the standard normal variant, mu is equal to 0, sigma square is equal to 1. So when that is the case, then what happens to this? The x happens to be a standard normal. When we call z as a standard normal variant, then I'm going to get the MXT of it as what? E raised to, you would be just having it as sigma square by 2 because mu is 0, this term vanishes, sigma square is 1, so I'm just left with, sorry, t square by 2, which is mu raised to t square by 2, and I'm talking about the standard normal variant. Okay, thank you.